Okay, today let's talk about formation of a differential equation whose general solution is given to you. So, suppose we have, again, I'm going to start with some, example equation. So, suppose we have x square plus y square plus 2x minus 4y plus 4 equals to 0. So, suppose this is an equation. It's a general equation of some sort of curves, right? Wherein you can actually figure out that these curves that I'm talking about are basically circles. Now, what kind of circles you can see? Try to create whole squares out here. If you try creating whole squares, clearly what you can see is you have 2x here. So with x square plus 2x, I think I can create a whole square of x plus 1, right? So x plus 1 whole square. And you have minus 4y here. So that means it has to be y minus 2 whole square, right? So y minus 2 whole square. So that means what has been used up here is x square has been used up, 2x has been used up. And what else has been used up? 1. 1 has been used up, right? So 1 has been used up. So if I introduce 1, then I have to subtract 1 as well. Similarly here, here clearly what has been used up? Actually nothing. What you have is 4. I can say that, y square minus 4y plus 4 itself gives you y minus 2 whole square, right? So that means when I introduced 1 and subtracted 1, so I'm left with minus 1 out here. So I can say that this equation is nothing but x plus 1 whole square plus x minus 2 whole square minus 1 equals to 0. In the next step, of course, you can get your 1 out here. So if the moment you get your 1 out here, can you see that you have an equation of a circle with center minus 1, comma 2 and radius 1. And similar to these, you can have more circles, with center minus 1, 2 with different radii, right? So this is sort of an equation which is giving you that idea that what kind of curves are we talking about. Now, circle, this we're talking about circle with radius minus 1, 2 and center minus 1, 2 and radius 1. If you differentiate this once, what do you get? Let's differentiate it with respect to x. And we will get 2x plus 2y dy by dx plus 2 minus 4 dy by dx equals to 0, right? Simple differentiation, nothing else, right? So simple differentiation, this is what I get. Okay, now what? Okay, so we've differentiated it once. So this is what I get, because when you differentiate 1, you will get 0. You just differentiated it with respect to x. And now let's find out what is dy by dx. dy by dx is minus of 2x plus 2 upon 2y minus 4. So you just collect the dy by dx terms here. Just collect the dy by dx terms here and take everything to the other side. And then whatever is your coefficient of dy by dx, that comes to the denominator. So this is what you will actually get. Now you can, of course, take 2 common. So clearly what you will get is minus of x plus 1 upon y minus 2. This is what we get. And you can even modify that. If you don't want a minus sign out there, you can modify it as 2 minus y in the denominator, where y should not be equal to 2, of course, because that's in the denominator, right? Now let's consider the equation x square plus y square equals to r square. That's a general. Now I'm trying to give you a gist of this kind of a situation. Now, if you give different values to r, you get different members of this family. This is a family of circles with center. You could have I could have taken family of circles with the center as minus 1 comma 2, which we had previously. Now I'm taking a simpler case where I'm taking a circle with center 0, 0. You can think of concentric circles where you have different r's, okay, different radii. They are part of the family of this kind of these kind of circles. Now, So what we're trying to say here is we want to generalize that what kind of differential equation will be satisfied. You can have x squared plus y squared equal to 1. You can have x squared plus y squared equal to 4, so on and so forth. We've taken 1, 4, 9 as an example because that gives you just, it's a simpler case. You know, these are simpler cases where you know the radius is 1, 2, 3, right? Now we want to find a differential equation that is satisfied by each member of the family, because I'm talking about a general kind of a differential equation here, right? For which, so if you want each member of the family to satisfy that kind of a differential equation, an equation with derivatives, and its differential equation is just an equation which includes derivatives. So what kind of equation will the members of the family of these kind of circles, you know, this kind of family, so which are basically circles, that each member satisfies that equation, differential equation. Now, for that, of course, it should be free from the radius r. The equation that you will be talking about will be free from the radius r. Why? Because if radius r is in consideration, then you know for particular r some other equation will be satisfied. For the particular r, some other equation is satisfied, right? So which is free from r. So if you differentiate, we are taking the simple case. Previously, I had taken up, where the center was not 0, 0. This is a simple case. Let's just differentiate with respect to x. So you have 2x plus 2y dy by dx equals to 0. And dy by dx clearly turns out to be as minus of x upon y, right? Similarly, so please try to understand what is happening here. So that this essentially is telling you that this is the differential equation. So all circles in the family x square plus y square equals to r square will satisfy x plus y dy by dx equals to 0, right? They will all satisfy this equation whatsoever. Similarly, so this was a case where I had taken family of circles. Now let's take a family of, say, straight lines, okay? So in the next example, let's take family of straight lines. So if the straight line, most commonly we take y equals to mx plus c, right? So this is a family of straight lines where your parameters are m and c. Now, again, you are looking for a differential equation. That is an equation that consists of derivatives, wherein what is happening? What is happening is that this equation should be free from the parameters. It should be free from the parameters. Why it should be free from the parameters? Because we're taking a general case. I want a general case, finding a differential equation that is satisfied by each member of this family. So I know dy by dx, simply if I find out dy by dx, it will be m, and d squared y by dx will be 0. So yes, the equation that will be satisfied by any member of this family would be that dy by dx is slope m and d squared y upon dx will be just 0. So this is the solution here. Now, procedure to form a differential equation that will represent a given family of curves. Let's work on the procedure now. So I just try to give you the gist how and what is essentially happening. What do you want to be satisfied, right? So number one, if the given family F1 of curves depends on only one parameter, it becomes very simple, because if it is dependent on just one parameter, then you will have to differentiate just once. So then it is represented by basically x, y, and a parameter a. So we're just talking about, x, y in picture. So x, y, and there is one parameter a. The moment you will differentiate once, this parameter will either go away or you can get a substitution for it. So the moment you differentiate once, for example, you have y squared equals to ax. Now you differentiate, you will get 2y dy by dx equals to a. So you get a value of A in terms of X and Y, right? You get a value of A in terms of X and Y. Here, just in terms of Y. But what you can do is you can definitely substitute back. So you differentiate it once, you will get an equation which will be involving X, Y dash, and A. What you can do is you can substitute for A. So what you can do is you can substitute for A. The required differential equation will be obtained by eliminating A, because you want a generalized solution. You don't want a particular A there. So you will just substitute the value of A and you will find an equation which will consist of X, Y, and just Y dash, because you had just one parameter. So Y dash is the maximum that you will fetch here. So these are the steps in case this is what you had. In case you have two parameters, then perhaps you know that one parameter, you cannot get two parameters with just one equation, right? You need two equations to solve for two parameters. So that is why you will have to differentiate twice. So if the given family of curves, say F, depends on two parameters, A and B, then it is represented by an equation of the form F2 xy, which is dependent on xy, A and B equals to 0, right? Now, you will differentiate. I'm telling you the procedure. So you will differentiate with respect to x, and you will get an equation which is, say, g, dependent on xy, y dash, you will get y dash in picture, A and B. Okay. But since you have A and B, just one equation will not help us further. So I'll have to perhaps differentiate once more. Since we cannot get value of AB with just one equation, we shall differentiate again. So we will differentiate again, and we will get an equation involving x, y dash, y double dash, A and B. So you will get a function which is dependent on x, y dash, y double dash, A and B equal to 0. You will eliminate A and B, and you will get a differential equation. You will eliminate A and B, and you will get a differential equation which will now consist of y dash, y double dash as well. So x, y, and y double dash as well. So you form different differential equations depending on what is the y that you have, what is the function, original function that you have. Suppose you have y equals to mx, the simplest case that I'm taking for a line. So dy by dx equals to m, and that's about it. So dy by dx is equal to m. If I get rid of m and just put dy by dx here, I have a differential equation which does not contain any parameter. So y minus x times dy by dx, or x times dy by dx minus y equals to 0. This is your differential equation. So you understand what we started off with? Now we are forming a proper differential equation. A differential equation a generalized form will not consist of any parameter. Similarly, if you have, say, a sine x plus b, remember, as an example, I had done it. Clearly, when we differentiate it twice, what do we get? We get minus a sine x plus b. Hence, we know that d2y upon dx squared plus y is equal to 0. And this becomes a differential equation. There is no parameter out here. You clearly just have d2y upon dx squared plus y equals to 0. Okay? So similarly, you can have different examples, like, for example, family of ellipses with foci on x-axis and center at the origin. So this would be something of this sort, I guess, if you try to picture it. So something of this sort, right? 0, 0, and x-axis is the foci, right? So the family of ellipses, in general, what is the equation of family of ellipses? So it is x squared upon a squared plus y squared upon b squared equals to 1. This is the general equation, right? Now, when we are saying that the foci is x-axis and center is origin, what does it mean? So it would mean that we are talking about situation Well, for first of all, for any family of ellipses, if you differentiate it, now you have two parameters a and b here. So if you differentiate, so you'll have 2x upon a square plus 2y upon b square dy by dx equals to 0. Or in other words, I have taken it in this form. I've taken x upon a square equals to minus y upon b square dy by dx. Okay. Now, we cannot be done because I have A and B in picture and I cannot do anything with A and B. So in other words, what I've done here is I've taken in the next, in the next, before differentiating it again, what I've done is I've just taken x, y, dy by dx on one side and just a constant on the other side. So that now when I will differentiate, whatever I have to use here for x and y, the right hand side will be just 0. So that's what I've done here. You differentiate again and you will get uh, using the product rule. Just use the product rule and you are differentiating y by x d2y upon dx square. So y by x as it is, derivative of the second, uh, plus dy by dx as it is, and then derivative of the first, which is y by x. So you'll have to use the quotient rule. So I've used the quotient rule here. And right hand side is just 0 because it was just a constant. So yes, so what's going to happen here? Just open it up. Just open it up. And you get x squared y by x. So 1x will cancel here due to y upon dx squared plus x times dy by dx whole square minus y times dy by dx. So this is what I get. So this is the equation which is being satisfied with the family, for the family of ellipses. For the family of ellipses, this is, or perhaps what I did was something wrong. And let me just correct myself. I think in my mind I took parabola, so I, instead of ellipses, I have taken parabolas. I'm so sorry. So basically, we're talking about family of ellipses, wherein the center is 0, 0. And that is why we have A and B out here in picture like this. I think in the next example, I've taken circles, and in one of the examples, I have taken actually parabolas as well. That's why I probably mixed it up. Whatsoever, having said that, so you get rid of A and B. You don't want A and B in the picture. What we are trying to say is that any ellipse from that family will satisfy this differential equation. That's what we are trying to say. So that's the base of differential equation. What is a differential equation? It's not a random thing. It's, some functions satisfying some equations which include derivatives. That's what is a differential equation. That's what we are always looking for in terms of solutions. So right now, what we have done is, what kind of function will satisfy what kind of differential equation? And slowly, steadily, we will start finding solutions for ourselves. Okay. Now, family of circles touching x-axis at origin. If you talk about circles touching x-axis at origin, that means the center has to be somewhere here. If this length is a, then this radius is a, basically, right? Because it's just touching x-axis at origin. It's touching x-axis at origin. That's clear. So any circle of this form will basically have radius a, right? And the center will be 0, comma a. Because y axis value is a, right? Your radius is actually y axis value for center, okay? And since it's touching 0, 0 at origin, it's touching, origin. It's touching the x-axis at origin. So hence the x-axis value will be 0 here. So 0, comma a is the center. That means an equation of any such circle will be x square plus y minus a whole square equals to radius square. Radius is a. So a square. So if you simplify this, what do you get? You will get x square plus y square minus 2ay equals to 0. So you just have one parameter. So if you just have one parameter, it's very simple. You can just differentiate once and you will find the differential equation, which will be satisfied by these kind of curves, these kind of circles. So 2x plus 2y dy by dx equals to 2a dy by dx. So dy by, you can find the value of a. Just make the substitution. You can find out the value of a, just make the substitution and you will know what is the differential equation being satisfied. So a is basically x plus y dy by dx upon dy by dx. So if you substitute in this equation of the circles satisfying this, so you'll have x squared plus y squared equals to 2ay. So 2ay means 2y into a. A is x plus y dy by dx upon dy by dx. You can cross multiply. That's what I've done. So when we substitute for a, this is what we get. And this, that means, is the differential equation, which is being satisfied. We can simplify it further if you wish to. You can take dy by dx, everything one side, and you have differential equation x squared minus y squared dy by dx equals to xy, where you cannot see the parameter a anywhere, right? So this is the differential equation which is being satisfied by all the circles in this family. Now, all the circles in this family. This is what is a differential equation all about. Again and again, I'm trying to tell you that a differential equation is basically an equation which contains derivatives. So you just need to figure out what is that function which will satisfy this equation. Okay. So we're just doing certain examples wherein we get to know, okay, if it's a family of circle of this sort, it will be satisfied by this differential equation and so on and so forth. Similarly, you have family of parabolas. As I said, I had this question in my mind because I had freshly done it. So family of parabolas having vertex at origin and axis along positive direction of x-axis. So that is, this is the case that I drew earlier. So if this is the case, then let a comma 0, because positive side of x-axis. So a is a positive number and 0 is vertex is 0, 0 at origin. So a0 is the focus of a member of this given family of parabolas. Okay. Now equation of any such parabola will be, what will be the equation of any such parabola? So you need to understand that the equation of parabolas, you need some basic knowledge of equations of circles, parabolas. So y squared equals to 4ax, because it is on the x-axis, you can see on the positive side of the x-axis. So it is y squared equals to 4ax. Again, you just have one parameter here. So differentiate once, you will have 2y dy by dx equal to 4a, which means a is simply y by 2 dy by dx. If you substitute back a out here, you will get an equation which will be getting satisfied. So y squared equals to 4y by 2 dy by dx to x. That means 2yx dy by dx. Y squared equals to 2yx dy by dx, which you can again further simplify. And what will you get? You will get, 1y cancels and you get 2xy, or you can just take it to one side, 2xy dy by dx minus y squared equals to 0. Or further, you can write it as y squared minus 2xy dy by dx equals to 0. So this is the kind of equation which will get satisfied by any member of the family of these kind of parabolas. This is how you frame equations which are basically being constructed, which are basically, you form differential equations for a particular family of curves. So this is how you can find it. Next, we'll be talking about methods of solving first order, first degree differential equations.